we put together a few questions which we hope to inspire some discussions following the questions. So, yes, we copied from Joanna's brilliant idea. But look at that URL. Let's type in some questions and answers.
So let's just start. This is it should be the last one, but well, it starts by this one. Let me see. Anyway, we thought that it would be interesting to do a survey, because this is a simulation session, about which is your favorite code, or the one that you are using the most. Or maybe you are using, but you don't know with which code you run. They run the simulation, so just answer as honestly as you can. Yep, it looks like. Anyway. Or maybe it will finish now with this one. We have 11 answers.
Click your favorite one.
You can, it's multiple choice, you can choose more than one if you use several. I was especially asked by Oscar Gerst what that basically means the best code ever, but well.
Rames, is it the Rames code?
Oh, it's Ramses. Oh, I also misspelled the...
Rames code.
Anyway, Ramses. Good. So we are almost done. So if somebody else...
The results.
2 more people, no? Okay, let's go.
Oh, wow.
Okay.
Oh, wow.
It's quite expected for Gizmo and I would say. And also interesting that we have some people that really don't know the code that has been used. Is anybody willing to comment? Why are you specifically using one of the codes? Or you want to comment anything related with the fact that you use simulations without knowing the code that has been used? No? Nobody? Yep, David? Yes, please.
Sandy and I, for example, are using various codes and simulations, but I don't know exactly which of the list that you gave there. For example, we use TNG 50, TNG 100. You know, we've looked at, I think, some Horizon. I've seen things from Vale, etc. But I don't remember what Joel tells me which code he's been using, so and I don't care. I know, but I don't know that. I'm just saying that. That's what I thought it was based on what I've heard, but I can't tell you for sure. I would not tell a student I use.
In any case, I would like to comment that it's interesting that and probably there's a lot of people that use this simulation without knowing the code. And it's important because sometimes you need to know details of at which level the codes can really be trusted, no? So it's quite significant. Yeah. If no more questions, because we are already quite late in time, I think we can move to try to see if we can get the other questions. Next, Paul. Okay, now we start with the first one. So, related with dark matter, that is what was about the first days of this conference. Yep, let's choose. You can also choose multiple options. And it would be great if you can comment why later on. Okay, we can close. There's one person that, perfect, everybody voted. Let's close the poll and let's see the results. Okay, interesting.
People still like CDM.
Yeah, good. And I think it would be curious to know the warm dark matter and the other, and maybe also the fuzzy, if you want to comment. So well, anybody can comment, but especially the outliers, let's say, if somebody wants to comment.
I wonder why people don't like warm dark matter so much.
Yep.
Warm dark matter is supposed to fix some of the problems, right? Why would you prefer CDM over warm dark matter? Of course, depends on the mass of the warm dark matter particle. But
Is there a signal cost that made warm matter,
well, maybe we haven't put in enough effort in in analyzing them, but that's true. It's true. Yes, people have not talked about that very much in this conference. In fact. There is, of course, constraints from Lyman Alpha Forest saying
I'm
that
assuming that-
warm dark matter mass should be above 4 keV or so. But as long as you satisfy that mass limit, it's still a viable model, and it will reduce some of the substructure issues. So it may be a bit more favorable if that still holds.
I'm so biased, I just use this conference as my way of keeping up with
Of
the
course,
field.
there's another camp that says astrophysical processes can actually solve the CDM problem, therefore you don't need the warm dark matter, but that's another option, but it's an unsettled problem.
Still, this person wants to comment, which is the other possible approach?
Is there anyone in here that's doing warm dark matter simulation and doing the analysis? Okay, Robert, do you want to comment on your efforts and see how you feel? Could you pass the microphone?
Ken, I think you summarized it well. I think they're still, it's still plausible. It's so it's not excluded. Of course, the warm dark matter mass is now a bit more massive than we would perhaps have liked to have, let's say, dramatic effect. So the effects will be much more subtle now. The other one, I mean, there's many other dark matter models. Good atomic dark matter. I mean, you can essentially, then it's like an infinite parameter space, right? But I think it's still very interesting to explore it, right? So I don't see a reason. I mean, obviously, CDM is the baseline, and I hope most of the effort should probably go there. But I think it's wise to keep other avenues open.
Yes. I think there was one talk that talked about the low mass galaxies closer to reionization epoch. So if you actually go push the redshift frontier further back in time, and you start to see the first galaxies, abundance of those galaxies will have maybe impact on warm dark matter nature. So it'd be good to reject them. Joel, you look like you have comments. Okay. All right, let's go next. Yes.
Okay, as you can see, we are going back and forth in the different days that we have been here in the conference. So now let's go back to the modeling of the IMF population 1, 2, 3 high redshift. So
Will results from new IMF modeling, both of the local universe POP1, POP2, and high Z POP3, change the currently used subgrid physics in low-res simulations?
we have 24. Somebody else wants to 25, 26. There. Okay, good. Let's go. I was really expecting this one. Good. Anybody wants to comment on how? Because yeah, the thing is that, well, it will probably change, but how? And any comment?
Of course, in principle, if we have the star formation physics properly implemented in simulation, we do not have to tweak these physics anymore, because star formation is actually dependent on maybe metallicity, and if we have a good physical model for star formation that depends on metallicity, this will actually naturally come out from the numerical simulations. So it's supposed to be an outcome rather than an input eventually, but right now it's not an outcome, it's an input for us right now.
Is in fact this no in line of what Ken is saying, that maybe the things will not change is already incorporated maybe in the current shock-free physics. So who is the one, well, yeah, if the one that said no wants to say anything.
Okay, we can go next.
Yeah, totally. Mm-hmm.
This one I wanted to ask more. There was one time the discussion about the Milky Way speciality. Is it special or not?
Okay, we are almost there. 6 more. Who wants to comment? Mm-hmm. No? Yeah? Okay. Okay. Mm-hmm. Interesting.
I thought during one of the talks somebody commented, maybe it was David, that said that the Milky Way, people finding the Milky Way is very special. Was it the comment? I forgot exactly, but I thought it was you who mentioned this. Do you want to say a bit more on this, elaborate? Or maybe Sandy, was it? I'm not sure. But somebody said there is evidence that the people are actually starting to realize more and more that Milky Way is actually a special galaxy. Maybe it was you, John.
I don't remember saying it, but I can mention lots of ways that the Milky Way is special. Andrew Wetzel has actually particularly emphasized that it formed unusually early. It has an extremely thin disk compared to most other galaxies. It's located in an unusual location for such a massive galaxy, namely the center of a cosmic sheet, a relatively small cosmic sheet, along with the Andromeda galaxy quite nearby. Most galaxies of Milky Way's mass are in filaments or closer to nodes. So that's another way it's unusual. And there are various other ways. So black holes are unusually small. Yeah. So the Milky Way, the reason that's important to take this into account is that because it and Andromeda are so nearby, they're the basis of a lot of detailed studies. But it's important not to draw general conclusions. Look, another example is Saga. Milky Way and Andromeda are both outliers from the Saga survey. The nearby satellites are more quenched in the Milky Way and Andromeda than in most other Milky Way mass galaxies. So, I mean, it's easy to think of a number of ways that the Milky Way is unusual. So, lesson, be careful about drawing general conclusions from studies of the nearby universe.
LMC, SMC.
Satellite
The
issues.
distribution of the satellites are also usual. I'm just saying there's enough that makes me suspicious. I
Mm.
give you that choice. My suspicious rather than yes.
And for the ones that think that no, which is because you think that there is no strong evidence, which evidence are you thinking on that should be conclusive? So why is anybody that said no that wants to comment? Why? It's a lot of people, huh?
For the young people, of course, the new Gaia data is giving us a lot of new dynamical information about the stellar orbits of the stars. And pretty soon, PFS, that's going to be operating on Subaru, is also going to do nearby cosmology much better than the previous surveys. So there's a lot of data that you can play with very soon. Okay, so we go next?
Yep.
Maybe? Is there any aspect, physical implementation, you would like to have it?
This is from like.
This is from the Agora standpoint, I guess.
Mhm. Yep.
Relate to last talk, I guess. which one would be most important? Maybe that's good to think about. Magnetic fields, cosmic rays, radiation transfer. What would you work on?
3 more people that wants to vote. Okay, well, I'm a bit scared of this one. Let's see. Okay.
Oh, magnetic fields wins. Okay.
Good, good. So we were already talking about that during the coffee break. Jihun, you know, we have some pressure now. Good. From the audience, I also think it's interesting because these ones, it's pretty things that should come next, no? And we already have been talking about it. But this one, so who? Is these people willing to comment?
What other?
Which? Yeah. Joanna.
Since my student has been working on the formation of giant clumps and what the things that affect the formation of clumps, that would be something to compare between the different projects, if anyone's interested.
Good. In fact, there was an idea of the clumps paper. It was discarded some time ago because of the lack of computational power, no? But maybe now with the new codes and new performance, we could just revive it. It was planned to be driven by Daniel Severino, in fact, the clumps paper. So yes, it's...
Also, we have to do a more massive sample, massive galaxies, which is more expensive than the dwarf one. So that's why it's kind of prohibitive. But
The resolution of the Agora cosmobron was 80 parsecs or worse, but not significantly better than 80. And the view in the community is that that's not good enough for formation of giant clumps to be reliably simulated. And to run at 20 or 30 parsec resolution would take a lot of computer time.
10 parsec would be nice, of course. But yes. Even now, of course, there's 1 plus d factor. So if you go back in time a little bit, we have 80 parsec co-moving. So if you divide by 1 plus c, it's a little bit better at redshift 5, for example. But
the Auriga simulations are in the right ballpark, possibly. And it would be interesting to look at them and see if they have giant clumps.
anyone working on the Auriga simulation analysis here? No one? Okay. All right, let's go next.
Auriga is Arepo, by the way. If somebody sorry. Is this somebody or is just a statistical thing? Oh, okay. Good.
Ji-hoon tortured himself too much during 2012 to 16. Okay,
Good.
let's go next.
Good.
Do you agree that the missing satellite problem is fixed, solved? Let's see how people feel this. I'm curious to see the results of this one, see how the younger generation's feeling about. Okay, come on, 3 more people.
These 2 last people. Okay.
All right.
There is always people jumping out. Okay.
Good. 50% feels it's solved. Anyone disagree?
For these ones, go back to the presentations and look at the Min-young's talk about... Min-young's, no, to the Ji-hoon's and Min-young's paper. Yeah.
Well, there's 10% that says no still.
Mm-hmm.
Do you have strong opinions who said no? Still have doubts? Okay, we don't know. But
Oh.
okay, come on.
I obviously
Oh, you
vote-
are the non-believer within the community.
I voted yes, but I mean, there are a lot of things that we still don't know about star formation, and maybe if we change star formation efficiency to reproduce high redshift, we again reproduce the missing satellites problem. So maybe is what the people
That's
are
it.
the people thinking
Yes,
about
sure.
the no.
It's not 100%
Yeah.
secure. Yes, that's true. That's true.
And the ones that answered this one, the too much satellites problem, it's true that some of the codes are having this problem. So anybody wants to comment about the too much satellites problem?
Well, observation is fine in too many satellites. Oh, you want to comment, Colin? Can you give the mic?
So because many people are trying to to match the high Z observational data. So I guess that they increase the transformation efficiencies or increase the adding of top-3 physics. So I just wonder that whether this kind of improvements are harmful or or not to the the number density of the UFT regimes. So although this in this area the number count of the observed UFT is poorly constrained, but I really want to know whether they tend to overpredict the amount of UFTs in Milky Way-like galaxies.
Okay. All right. Anyone?
I chose that one because I'm getting the sense that among the dwarf community, they're finding a quite variety of dwarfs, diffuse things and this and that. And it seems like some of those have very particular paths, and I don't know how they get them. They didn't give me the demographics, but it seems like that maybe there are too many compared to some simulations, but I don't know. I mean, you guys who do the work should tell me whether diffuse galaxies, for example, are fully explained by all the simulations. I don't think so.
Yes. Yes. Of course, dwarf galaxies are difficult to simulate for numerical simulators because it requires high resolution. And cosmologically, it's also tough to bring that down to z equals 0. So only now maybe we're beginning to get good handle on the dwarf galaxy formation in numerical simulations. You want to say something about dwarfs? No? Okay, good. So let's move on maybe. A few more. Maybe is that?
Or is the last? Or
Last
is the
one?
one before the last?
Okay, before the last. Depends on how successful Ramon's talk was, I guess.
Okay, another person. One more? No? Right. Then let's start.
People still skeptical about the planes. Ramon, you want to say something?
Actually, I vote the third option. I think that the Milky Way is still like a bit weird in the case of the planes of satellites. For example, the most massive satellites in the Milky Way are the ones defined in the plane. That is something that I think that in simulations we are not still. And yeah, so for like. But maybe we can explain that with different factors. For example, the last major could be affecting that. But in the Milky Way, we also are in a sheet, and we also have like a huge satellite as the LMC, bringing their own satellites. So probably if we move the efforts there, we can explain. But I think that it's still a bit weird. We are on the way to solve it, but I don't know what people thought.
What is the prospect of doing this for other galaxies, not Milky Way? Can you give?
Yeah, I think that there are efforts there trying to understand like the radial velocity of our satellites, and if we look some V modality of some satellites moving towards and forwards, but I think that we cannot do like so detailed study as in the Milky Way because we don't have the kinematics. Even in the Milky Way with Gaia data, it's too difficult to like constrain the angular momentum of our satellites. So I think that it's going to be hard, but yeah, we can do something.
In
In
a
Saga,
sense-
I think that they did something and they didn't find planes of satellites so prominent, but I'm not pretty sure.
Yeah, there are the two definitions, no? The geometric and the kinematic. For the geometric, Euclid will give probably many more in external galaxies. But yeah, for the kinematic ones.
Okay, we can
Yep.
maybe
Let's see if there is a last.
finish the last one.
Uh-huh. Yeah. That is quite related with this future dwarfs project in Agora, but also there is Edge project and several other projects trying to produce more and more realistic dwarfs. So again, we put it only some options. If you have any other, please just say that on the discussion. Okay. Four, six, more people. Nobody else wants to. Sorry for adding pressure. Okay, good. Let's. Oh, yeah.
Okay. Self-regulation at high Z. Okay, anyone wants to comment on this topic? Ask question?
How many people is here working on this kind of
Realistic dwarfs.
year? Nobody else directly?
Well, I actually... Oh, sorry. Yeah, Colin maybe?
I forced you to comment. You can comment. What are you?
I mean, I actually have a question. Like, is self-regulation at high redshift a problem for dwarfs? Like, that's when we form most of the stars in these
Mhm.
systems, right? So, I don't know. Like, they need to.
But
grow.
dwarfs have known to have recent star formation too, right? They're actually blue ones.
Oh yeah,
un-
no,
unless-
just most. They're saying like that's when they form most of the
Yes.
stellar mass.
Uh-huh.
Mhm.
So, but like, you give me a mic so I can say. Like, I don't think it's even. I voted it, right? But like correct reionization recipe, I think we actually want to have dwarf galaxies evolve in an environment that actually reionize following the properties of the environment. So I don't think we can do recipes. I think we have to reionize self-consistently.
Mhm. Of course, yes, reionization.
In fact, Hartley showed the whole evaporation
Mhm.
of the inflows.
Yes.
Okay.
Comment? No? I actually wanted to ask Viraj, who gave a nice talk about JAX and all this parameter inference using differential such. That would it work also for the dwarf galaxy inference, not just the Milky Way type stable massive galaxies?
Yeah, I mean, so actually, what we've been doing so far, we limit ourselves just to Milky Way and dwarf scales because we've been focusing mostly on stellar feedback. So I think one interesting thing, which I ended my talk with, was how would you, if someone told you like the resolved small scale ISM simulation community or these new Sapphire inference results or observations gave you constraints that you are not allowed to, have mass loading factors of 1,000 for dwarf galaxies. Can you make a dwarf galaxy without that? And we know it's possible in some high resolution simulations with certain feedback schemes, but yeah, I'm kind of curious what the space of plausible solutions is. If you cannot eject 1,000 times more mass than you formed in stars, then what mechanisms do you have via cosmic rays or whatever to prevent accretion in the first place? You have to stir turbulence in the CGM. You have to have a lot of non-thermal pressure support that holds the CGM up, prevents it from accreting. I don't know, but I'd be curious to talk about that.
I don't know if you're asking about this in light of the recent observations from some observers going to like mass loading factors and saying 10 to the minus 3, super, super low, no outflows. I was looking into that specifically for dwarfs and how the outflow in mass from these systems is inferred. And one of the things that I was very puzzled about is that they assume a typical density of the outflow that is on the order of 10 to the 3 atoms per cc. That is extreme. I doubt that these dwarfs even have environments like that. This is actually extrapolated from the sulfur line ratio. Long story short, if you actually grab any simulation, at least from my models, with any physics, and you generate mock observations and do the treatment to infer the outflow in rates, you actually recover exactly the same as the observations are basically giving you, no matter the model. So I think you're at freedom of having mass loading factors and energy loading factors at least for these systems. But maybe there is an observer that can comment on that.
I'll just quickly also say, I mean, I agree with you. So I don't take the observations that exist as the gold standard either. So I agree, like there's also concerns about like people report outflow rates based on H alpha, but that's one phase. So yeah, I mean, that's part of the problem. Like we're entering big data, but really we have such a ill-constrained problem because there's so little information, even with the CGM data, especially at the galaxy and dwarf scales. So yeah, I don't know. But that's why I think we need these statistical type, like, yeah, we have the freedom and do posterior predictive checks and make very specific predictions for what metals could be worth measuring. So I mentioned there's this degeneracy between metal loading and mass loading. So you have to maintain some kind of continuity equation for metal and overall mass evolution. So yeah, I'm just rambling.
Yeah, I was the other, and as an observer from many decades, there are all kinds of dwarfs out there. First of all, there's a huge variety, so that's just like categories like, oh, what do you want to study about, say, small animals? Well, there's so many different kinds from insects to da-da-da. I think it's the same for dwarfs. I mean, I've not heard a single talk in which people talk about tidal dwarfs, for example, things that result from tidal interactions, things that form that people call dwarfs. Maybe someone tells me, no, they're just clusters. But the point is that there's a huge variety of dwarfs. They each have many, and among them, there are probably different paths for them. So I feel that, the biggest challenge, first of all, we don't even have the classification of dwarfs yet. Divide them among different clients, and then go and say, here are the simulations that will address this subcategory. So until the dwarfs are categorized, I feel that's a little premature to talk about, what's the biggest challenge. So I'm at a very early stage of this whole process. You're an observer.
Actually, on that note, I want to just also quickly mention again, so because we're talking about dwarf galaxies and challenges for simulation, so based on stuff that Ha-Wen's done, I've done, Farhan showed in his talk, Robert Feldman showed, James Bullock showed, a lot of large volume simulations, they're not reproducing the high fractions of early elongated prolate galaxies inferred from observations with JWST and Hubble. So is that a resolution thing? I don't trust many of the simulations at high redshift for this problem because some of them, like TNG, have gravitational force softenings of hundreds of parsecs, and that's a typical size of these early elongated galaxies in the data. So I don't trust the star particle orbits, and I don't trust the 3D shapes. But is it just a resolution thing? Is it a cosmology thing, a dark matter thing, feedback thing? I don't know. Yes. I mean, so we do it different ways. One way is I can do it completely empirically. So I can inject fake galaxies into my imaging, and I can ask to what limit am I sensitive to like face-on disks that should have been there if all these elongated edge-on things were actually edge-on disks. And we are very sensitive.
What if you assume that these JWST observations are of very clumpy systems, with most of the brightness coming from a small volume or area of the galaxy. And actually that area also might not have most of the mass. Maybe the clumpiness is actually driving the oblate shapes.
But I mean, I'm kind of agnostic, although I have constraints. I mean, so the total masses of these systems that we see that are preferentially elongated, they're like 10 to the 9, 10 to the 10 in stellar mass at redshift 2, 3, 4. And you would need a very, very large extended disk that seems not viable in the early universe where you have mergers and stuff. And I was just going to say, the other thing Hongwen's done in this paper in 2019 is you can take actual galaxies in your simulations, you can take actual observed elongated galaxies that you see in your data, and you can deproject them and reproject them into the face-on configuration, recalculate the surface brightness, and at most you would have missed, 20% of these galaxies face-on disks at high redshift, extended large disks in this mass redshift regime. And with JWST, that number is even smaller, because JWST goes 2 orders of magnitude deeper than HST. So I don't know. Another way to get a handle on this is the intrinsic alignment stuff also, because the stuff that Farhan showed, you expect correlation spatially between the orientation of these things if they're tracing out filaments. So it's a test, but very hard either way.
Okay, thanks for the comments. Any other things that anyone wants to comment on? I think time is pushing a little bit. That was the last question, I guess, right?
Yep.
Yeah. So shall we wrap up?
Totally. Yep. So.
Okay. Okay.
Yeah, so thanks. Yeah, I just want to say a couple things. I think Joel as well. So first off, thanks for coming and thanks for staying. I think it's been a successful workshop, but it's great to keep doing it, and it's really successful because of all of you for great talks and great discussion, both the sort of formal discussion like this and informal discussion over lunch and coffee and dinner. Joanna actually took a look at the participant lists from the last 10 years. So we've got about 430 people have come here, many multiple times. About 10 have come every year, which is great to see. So I want to thank everybody for that. It's been really successful for a lot of people, and I really want to extend a big thanks and round of applause to both Joel and Avishai, who are really the driving force behind all of this. And then some people who've helped out a lot this year. So Joanna's been keeping Zoom running for people attending by Zoom and helping with all the projections. Zach, who's in the back room, I think. I don't know if he can hear me, but if somebody pokes their head in and asks him to stick his head out, we can thank him. He's been keeping all the technology running and doing all the recordings, so the talks will be up on YouTube at some point relatively soon. And then we have the student helpers who've been keeping all the logistics going, who are sitting in the back and have been here all week. So that's Ira and Lizette and Scarlett and Shinrun. So all of the sort of making sure food is working and name badges and all that, they've really been helping a lot for all of that. So thank all of them as well. And say thanks on your way out.
Well, the only one left to thank who didn't get mentioned is Colin DeGraff. Thanks again to all the participants, especially the discussion leaders who often rather imaginatively made the discussions interesting and fun.
Yeah, I think
Goodbye.
So there is, unless it's been moved, but there should still be coffee, tea, snacks,
No,
and things
I
out
think
there?
it's been removed. The last I looked, there were bags of
Okay.
lunches that may still be out there.
So for those of you here next week, have a good week. I will not be, but have a good time. For those of you not here next week, have a good trip back.
Yeah, as far as for next week, Joanna sent out an email asking people to sign up if they want to meet. We will have a session in ISB 221. That's the building that the physics and astronomy people are mostly have their offices in. And 221 is a nice room it opens onto the courtyard. And we plan to meet around 11 on Monday, everybody who's interested. And one of the things we'll do is discuss if we want to have any more talks or more discussions, and if so, when. And so please, if you're interested, come by around 11 a.m. and we'll sort of plan activities for the next few days starting on Monday. Of course, on Saturday, the Agora team is going to be meeting in that same room, ISB 221, starting at 9 a.m. with a light breakfast, and then going all day long on all of these interesting projects that we're finishing and new ones that we're starting for the Agora. Okay, safe travels, everyone.